Hello friends, welcome to my lecture on Cauchy Euler equations. The differential equation of second order x square by double dash plus ax by dash plus by equal to 0, where a and b are constants, is known as a Cauchy Euler equation. Now you can see that this is a second order linear differential equation with variable coefficients. The coefficients of by double dash is the coefficient of by double dash is x square, the coefficient of by dash is a into x. So the coefficients of the derivatives are functions of x. Now in general, an ordinary second order linear differential equation with variable coefficients is not easy to solve, but some special class of second order linear differential equations with variable coefficients can be solved. So this Cauchy Euler equation belongs to one such class of differential equation, where you can see that the power of the monomials, say x square, the power of x square is 2 and the derivative by double dash is of second order. So and similarly in the second term the power of x is 1 and derivative is of first order, and then we have v into y equal to 0. So in every term the power of x and the order of the derivative in that term are same. So such kind of differential equations are called as Cauchy Euler equation. So we are taking a first homogeneous case of, actually this is a homogeneous case of Cauchy Euler equation. Now such type of equations can be reduced to linear differential equation with constant coefficients, and we know how to solve a linear differential equation with constant coefficients. So by making the substitution, say z equal to ln x, by making the substitution z equal to ln x, we shall convert this equation to Cauchy Euler equation, to ordinary linear differential equation with constant coefficients, and solve it there, and then replace the variable z by x. So let us put z equal to ln x in this, let us consider z equal to ln x. Now so we are changing the independent variable from x to z by considering z equal to ln x or x equal to e to the power z. So when you take z equal to x equal to e to the power z or z equal to ln x, let us find the values of the derivatives of y with respect to x. So when you find dy by dx, we can write dy by dz into dz by dx, and dz by dx you can see from here z equal to ln x, that it is 1 by x. So we have dy by dx equal to 1 over x dy by dz. Now so dy by dx we get as 1 over x dy over dz, and now let us find d square y by dx square. So d square y by dx square is nothing but the first derivative of dy by dx. dy by dx we can put from here. So d over dx of 1 over x dy by dz, and this is equal to now this is a product of two functions of x. So we can find the derivative of this product. So derivative of 1 over x is minus 1 over x square dy by dz, and then 1 over x times d over dx of dy by dz, and dy by dz can be put as d over dx of dy by dx equal to 1 over x dy by dz. So we can write as dy by dz. So d over dx this is minus 1 over x square dy by dx and dy by dz, and then 1 over x dy by dz, sorry wait a minute, this is okay, dy by dx, okay. So this is minus 1 over x square dy by dz, and then here I can write 1 over x d over dz dy by dz into dz by dx. Okay, right, that is okay. So 1 over x square dy by dz, and dz by dx we know dz by dx is 1 over x. So 1 over x square dy by d square y by dz square. So, we get 1 over x square times d square y by dz square minus dy by dz, or we can say x square d square y by dx square, x square d square y by dx square equal to d square y by dz square minus dy by dz. Now, let us denote the differential operator d over dz by d. If we denote the differential operator d over dz by d, then dy by dx will be 1 over x dy, or we can say x dy by dx will be dy, and d square by x square d square by dx square will be this will be equal to d square by dz square. So, d square by minus dy, which is same as d into d minus 1 y. Okay. Now, so then the equation 1 can be written as, the equation 1 you can see this is equation 1. So, x square by double dash is d into d minus 1 by a times x by dash is dy, and then we have plus by equal to 0. So, we get the operator d over d minus 1 plus ad plus b operating on y equal to 0. Now, this is nothing but d into, so d square minus d plus a. So, plus a minus 1 into d plus b operating on y equal to 0, which is a linear differential equation with constant coefficients, where the independent variable has been changed from x to z, and it can be solved by the method of linear differential equation with constant coefficient, which we have already discussed. So, we can find the solution of this equation and then replace z by ln x there. Now, there is another method which is rather simpler to find the solution of the differential equation x square by double dash plus ax by dash plus by equal to 0. In this method, we put by equal to x to the power m in that equation. So, we will get x square by double dash. When you differentiate twice x to the power m, you get m into m minus 1 x to the power m minus 2. So, you get m into m minus 1 x to the power m after you multiply by x square, and similarly a times x by dash will be m into a x to the power m plus b x to the power m equal to 0. So, that is what we have written here, x square m into m minus 1 x to the power m minus 2 plus a x m x to the power m minus 1 plus b x m equal to 0. Now, since x to the power m is not equal to 0, when x is not equal to 0, we shall get from this equation m into m minus 1 plus a into m plus b equal to 0, which is nothing but m square plus a minus 1 into m plus b equal to 0. Now, this is a second order, this is a quadratic equation in m, and if we find the roots of this, if they are say m1 and m2, if they are distinct roots, then you get by one solution of the given differential equation as by 1 x equal to x to the power m1, and the other solution as by 2 x equal to x to the power m2. Now, m1 and m2 are distinct, so by 1 over by 2 will not be a constant, and therefore, x to the power m1 and x to the power m2 will be linearly independent to each other, and so we can write the form a fundamental system of solutions of the given equation for all x for which they are defined. Okay. So, general solution of the equation in this case can be written as by x equal to c1 x to the power m1 plus c2 x to the power m2. Now, the other possibility is that the two roots m1 and m2 are equal. Now, we had the equation like this, the equation is m square plus a minus 1 into m plus b equal to 0. When we solve it for the values of m, we get minus a minus 1 plus minus under root so when the two roots are equal means when the discriminant is equal to 0. So, when a minus 1 whole square minus 4b equal to 0, we get the case of a double root. We get m1 equal to m2 equal to minus half a minus 1. So, in this case one solution we can write, that is x to the power m1 or x to the power minus half a minus 1. How to obtain the other solution? So, what we will do is we will apply the method of variation of parameters. So, one solution is this is 1 by 2 into 1 minus a, m1 is 1 by 2 into 1 minus a. So, one solution is by 1 to equal to x to the power half 1 minus a. Now, let us assume other solution by 2 to be some u times by 1, where u is the unknown function which is to be determined in such a way that by 2 is a solution of the given differential equation, second solution. So, u is some function of x. Now, let us substitute by 2 in equation 1. So, when we substitute by 2 in equation 1, since by 2 is a solution of that equation, we will get x square by 2 double dash plus ax by 2 dash plus b by 2 equal to 0. Now, let us see how we get u double dash x plus u dash equal to 0. Once we arrive here, we shall be able to determine the value of u very easily. So, let us see how we arrive here. Okay, so let us put our differential equation is this one. Our differential equation is x square by, so we have x square by 2 double dash plus ax by 2 dash p plus b by 2 equal to 0, and we have assumed by 2 equal to u times by 1, by 2 equal to u times by 1. So, let us find its second and first and second derivatives. So, then by 2 dash equal to u dash by 1 plus u by 1 dash, and by 2 double dash will be equal to u double dash by 1 plus u dash by 1 dash plus u dash by 1 dash plus u by 1 double dash. Okay, let us substitute these values of by 2 dash and by 2 double dash in this equation. We get x square by 2 double dash means u double dash by 1 plus 2 u dash by 1 dash plus u by 1 double dash plus a x by 2 dash will be u dash by 1 plus u by 1 dash plus b u by 1 equal to 0. Okay, now we have x square u double dash by 1. This is the term, this is one term which contains u double dash, and the term containing u dash is what? So, we get let us first write by 1 double dash terms. So, u times I think I will write, okay, u times x square by 1 double dash plus u times ax by 1 dash plus b by 1. What is left out is here we will write this as, so we have taken this term, we have taken this term, we have taken this term, we have taken that. So, ax u dash by 1, and we have this one 2x square u1 dash by 1 dash. So, u dash times two x square by 1 dash and then ax by 1 equal to 0. Now, let us see, since by 1 is a solution of the given differential equation x square by double dash by 1 double dash plus ax by 1 dash plus b by 1 equal to 0. So, since by 1 is a solution of this equation, we have x square by 1 double dash plus ax by 1 dash plus b by 1 equal to 0. Acha, okay. So, this term vanishes, and furthermore let us see, furthermore by 1 equal to x to the power 1 by 2 into 1 minus a. Okay. So, let us differentiate this. So, by 1 dash equal to 1 by 2 into 1 minus a x to the power 1 by 2 into 1 minus a minus 1. So, we get minus half minus a by 2, and this can be written as okay. So, 1 by 2 1 minus a into by 1 divided by x. So, we get x by 1 dash equal to 2x by 1 dash equal to 1 minus a into by 1. So, r 2x by 1 dash equal to 1 minus a into by 1. So, let us see what do we get now. Okay. So, this equation reduces to x square u double dash by 1, and then u dash, let us write x outside. So, u dash x, and then 2x by 1 dash, 2x by 1 dash is 1 minus a into by 1, and here we have a by 1 equal to 0. So, we will get x square u double dash by 1, and then this a by 1 will cancel, we will get u dash x by 1 equal to 0, or we can say now by 1 is x to the power half 1 minus a. Let us remove this by 1 and x. So, r we will get x u double dash plus u dash equal to 0. So, we get x u double dash plus u dash equal to 0. Now, we can easily solve this. When you integrate, you can write u double dash by u dash equal to minus 1 over x. So, integrating we get ln u dash equal to ln 1 over x, and which will give you u dash equal to 1 by x. So, we get u equal to ln x, and thus by 2 equal to u by 1 will be equal to ln x into by 1. Now, by 2 over by 1 is equal to ln x. So, by 2 over by 1 is not a constant, and therefore, by 2 is second linearly independent solution of equation 1. So, we have got two linearly independent solutions of the equation variable with variable coefficients, Cauchy Euler equation, and so the general solution will be by x equal to C1 by 1. By 1 is x to the power m1, m1 is, let us recall, 1 by 2 1 minus a, and then C2 times ln x into x to the power m1. So, this is the case of auxiliary equation having two equal roots. Now, let us go to the case where the roots of the auxiliary equation are complex, say alpha plus minus I beta. Now, as such, alpha plus I beta and alpha minus I beta are both distinct roots. So, we can write the two linearly independent solutions of equation 1 as by 1 equal to x to the power alpha plus I beta and by 2 equal to x to the power alpha minus I beta. But we are always looking for real solutions. So, what we will do is we will try to find two linearly independent real solutions of the Cauchy Euler equation. So, let us note that we can write sin x to the power I beta as x to the power I beta as e to the power ln x to the power I beta, which is equal to e to the power I beta ln x. Now let us apply Euler's formula. So this is e to the power I theta is cos theta plus I sin theta. So cos beta ln x plus I sin beta ln x we shall have. So x to the power I beta will be cos beta ln x plus I sin beta ln x. Likewise x to the power minus I beta, oh there is a okay, x to the power minus I beta is equal to cos beta ln x minus I sin beta ln x. And now so by 1 will be equal to by 1 plus by 2 by 2. By 1 is equal to x to the power alpha cos beta ln x plus I sin beta ln x by 2 is x to the power alpha cos beta ln x minus I sin beta ln x. So adding y1 and y2 we get 2x to the power alpha cos beta ln x, or we can say y1 plus y2 is x to the power alpha cos beta ln x, and y1 minus y2 divided by 2I is equal to x to the power alpha sin beta ln x. Now our equation is a homogeneous equation. So if y1 and y2 are two solutions of that, then y1 plus y2 and y1 minus y2 by 2I are also solutions of that. So x to the power alpha cos beta ln x and x to the power alpha sin beta ln x, they are also solutions of the Cauchy Euler equation, homogeneous Cauchy Euler equation. Now further we note that x to the power alpha cos beta ln x and x to the power alpha sin beta ln x, they are independent of each other, because when you divide one by the other it does not come out to be a constant. So they are both linearly independent, and therefore the general solution is can be written as by equal to x to the power alpha c1 cos beta ln x plus c2 sin beta ln x. X to the power alpha cos beta ln x and x to the power alpha sin beta ln x can be said to form a fundamental set. So this is the general solution in this case. Now let us take an example, x square by double dash plus 2x by dash minus 2y equal to 0, and let us see how we solve it. So x square by double dash plus 2x by dash minus 2y equal to 0. So let us put x equal to e to the power z or z equal to ln x. Then we have seen that x square by double dash is equal to d into d minus 1 by e, and where d is of d over dz, and x by dash is equal to dy. So let us put these values. So d minus 1 by plus 2 dy minus 2y equal to 0, or we can say d square plus 2 dy minus dy is dy plus d minus 2 operating on by equal to 0. Now this is a second order linear differential equation in the with constant coefficients. The dependent variable is by, the independent variable is z. We have d square by over dz square plus dy by dz minus 2y equal to 0. So to find the solution of this, we write the auxiliary equation. M square plus m minus 2 equal to 0, and the factors of this equation are m minus 2, m plus 2 into m minus 1 equal to 0. Okay, so m is equal to minus 2 and 1, they are the two distinct roots of this auxiliary equation, and therefore the general solution is y equal to c1 e to the power minus 2z plus c2 e to the power z. Now let us now from the variable z we have to convert to the variable x. E to the power z is x, so x square is e to the power 2z. So this is C1 x to the power minus 2, and then we have C2 x. So we get the general solution as y equal to C1 x to the power minus 2 plus C2 x. Now we can find the solution of this by that other method. So let us find the solution by the other method. Let us put y equal to x to the power m in the given equation. Let me call it as equation 1. Then what do we have? M into x square times m into m minus 1 x to the power m minus 2 plus 2x. Y dash is m into x to the power m minus 1 minus 2x to the power m equal to 0, or we can say m into m minus 1 plus 2m minus 2 x to the power m equal to 0. Now again x to the power m is never 0 when x is not equal to 0. So we get, since we have m square m into m minus 1 plus 2m minus 2 equal to 0, which gives you m square plus m minus 2 equal to 0. The roots are m equal to minus 2 and 1. So the general solution is y equal to C1 x to the power m1 plus C2 x to the power m2. This is the case of two distinct roots, and m1 is minus 2. So C1 x to the power minus 2 plus C2 x to the power m2 is 1. So we get C1 x to the power minus 2 plus C2 x, same as in the previous case. So this is how we will solve the Cauchy Euler equation in the homogeneous form. Now let us consider the Cauchy Euler equation can be generalized to such type of equations also, where we see that the power of alpha x plus beta is same as the order of the derivative occurring in that term. So here alpha x plus beta power is 2, and we have the derivative of second order. Here alpha x plus beta power of alpha x plus beta is 1, and we have the derivative of first order. So in such a case what we do is we shall convert this to Cauchy Euler equation. We can define z equal to alpha x plus beta. So when we take z equal to alpha x plus beta, we can find dy by dx and d square by dx square. So dy by dx here will be dy by dz into dz by dx, and dz by dx is alpha. So we write alpha times dy by dz, and from here d square by dx square will be alpha times d over dx of dy by dz. So d square by over dx square, this will be equal to d over dx of dy by dx. Now dy by dx is alpha times dy by dz. So alpha times, alpha is a constant, we can write it outside. Now this is alpha times d over dz of so this is dz by dx is alpha. So we have alpha square d square by dz square. So by defining alpha x plus beta as z, we can write this equation in the Cauchy Euler form. So we can, then we shall have alpha square. Okay, let me write alpha square. Okay, so alpha x plus beta whole square by double dash, that will be alpha x, that will be z square by double dash is alpha square d square by, where d I am now denoting by d over dz, plus z alpha y dash is so no, it is a, sorry, it is a. So z into a, then alpha, then dy and then plus by equal to 0, or we can say this is nothing but alpha square z square d square plus a alpha z d plus b operating on by equal to 0. Now, this is a Cauchy Euler equation in the independent variable z. Now, this can be divided by alpha square and we can bring it to the standard Cauchy Euler form, where the coefficient of z square d square by dz square is unity. So, this can then be solved by the methods which we have just now discussed, and then after finding the solution in terms of z, we can put z equal to alpha x plus beta. So, we will get the solution. Now, let us say, for example, let us look at this differential equation. So, for example, we have the differential equation 3x plus 2 by 3x plus 2 whole square by double dash, and then we have 3 times 3x plus 2 by dash plus minus 36y equal to 0. So, define 3x plus 2 equal to z, then dz by dx equal to 3. So, dy by dx equal to dy by dz into dz by dx. So, we get 3 times dy by dz, and d square by dx square is equal to alpha square. So, this will be 3 square. So, 9 times d square by dz square. Similarly, we get. So, we shall have 3x plus 2 whole square. So, z square by double dash is 9 times d square by, then we have 3 times z, y dash is 3 times dy, and then we have minus 36 y equal to 0. Now, we can divide this equation by 9. So, dividing by 9, we have z square d square plus dy plus d minus 4 zd by equal to 0. Now, this is a Cauchy Euler equation with the coefficients here 1 and here we have minus 4. So, it can be then solved by defining z equal to, so now the independent variable is z. Let us define z equal to e to the power t. Then we shall have z square d square by will be equal to, then z square d square by e over dz square will be equal to d square by over dt square minus dy by dt, and z dy by dz will be equal to dy by dt. So, we shall have, so we will get d square by dt square minus dy by dt for z square d square by plus z dy, we will get dy by dt, and then minus 4y equal to 0. So, this will cancel. We have d square by over dt square minus 4y equal to 0, which is a linear differential equation of second order with constant coefficients. So, the auxiliary equation is m square minus 4 equal to 0. So, m equal to plus minus 2. So, we get the general solution as y equal to C1 e to the power 2t plus C2 e to the power minus 2t. Now, let us put t as ln z. So, C1 e to the power 2 ln z plus C2 e to the power minus 2 ln z, and this is equal to C1 z to the power 2 plus C2 z to the power minus 2, but z is equal to 3x plus 2. So, we get C1 3x plus 2 square and C2 3x plus 2 minus 2. This is the general solution in this case. Now, let us take a non-homogeneous Cauchy Euler equation. We have seen how to solve Cauchy Euler equation in the homogeneous form. So, let us just find the particular integral. So, what we will do is, let us consider x square by double dash minus 3x by dash plus 4 by equal to. Now, we have to remember one thing here. When we solve a Cauchy Euler equation in the non-homogeneous form, the method where we put x equal to e to the power z, that is applicable here in the case of non-homogeneous equation, but the other method where we have put y equal to x to the power m, that is not applicable here, because y equal to x to the power m does not reduce the Cauchy Euler equation into a linear differential equation with constant coefficients. So, y equal to x to the power m method can be used only in the case where the Cauchy Euler equation is in the homogeneous form, but x equal to e to the power z can be reduces the Cauchy Euler equation to linear differential equation with constant coefficients. So, that will be applied to solve non-homogeneous Cauchy Euler equations. So, let us put x equal to e to the power z. So, then we will have d into d minus 1 y minus 3 dy plus 4. Okay. So, x is equal to e to the power z. So, we get 2 times e to the power 2z. Let us change the right hand side also to z. So, we have d square minus 4d plus 4 by equal to 2 e to the power 2z. Now, auxiliary equation is m minus 2 whole square equal to 0. So, m equal to 2 2. So, we get case of complex roots. So, by c x in this, by c z, because independent variable is z. So, by c z will be equal to c1 plus c2 z e to the power 2z. Now, let us separate z equal to ln x. So, we get the complementary function c of s c1 plus c2 log x into x square. So, this is the complementary function. Let us find the particular integral. So, particular integral is 1 upon d minus 2 whole square operating on 2 times e to the power 2z. Now, 2 is a constant, we can write outside the operator. E to the power 2z, when you replace d by 2 here, it becomes 0. So, what we do is 2 times 1 over d minus 2 operating on e to the power 2z. Now, let us apply the formula 1 over f d e to the power ax into b, that formula let us apply. So, e to the power ax comes out, we have when b is a function of x. So, in case f d becomes 0 on replacing d by a, we apply this formula. So, this is equal to 2 times 1 over d minus 2, this will be e to the power 2z 1 over d plus 2 minus 2. So, d operating on 1. This means 1 over d means integral of 1. So, we get z. So, e to the power 2z into z. Now again e to the power 2z into b, this is b, so we get 2 times e to the power 2z 1 over d plus 2 minus 2 operating on z. 1 over d when operates on z we get integral of z, so 2 times, so z square e to the power 2z. Writing z in terms of x, we write z equal to ln x, so this is ln x whole square and e to the power 2z is x square. So this is particular integral ypx, this is ypx. So general solution is y equal to c1 plus c2 ln x into x square plus x square ln x whole square. This is how we solve this equation. And the one more differential equation we have taken, let me just give a hint here, because no formula will be applicable here, we have to apply the general method to find the particular integral. So x square by double dash plus 3x by dash plus y equal to 1 over 1 minus x whole square. So again let us put z x equal to e to the power z. So then d into d minus 1 plus 3d plus 1 y equal to 1 over 1 minus e to the power z whole square. Now this is d square minus d, so we have d square plus 2d plus 1, so auxiliary equation is m square plus 2m plus 1 equal to 0, which is m equal to minus 1 minus 1. So complementary function will be c1 plus c2 ln z, c1 plus c2 z and then e to the power minus z. Converting to x, we have c1 plus c2 ln x, x to the power minus 1. And for particular integral what we will do is, so particular integral is equal to 1 over this is d square plus 2d plus 1, so d plus 1 whole square operating on 1 over 1 minus e to the power z whole square. Now this is 1 over d plus 1 into 1 over d plus 1 operating on 1 over 1 minus e to the power z whole square. So let us first find the effect of 1 over d plus 1 operating on 1 over 1 minus e to the power z whole square. So 1 over d plus 1 when operates on 1 over 1 minus e to the power z whole square, what we get is e to the power minus z integral e to the power z into 1 upon 1 minus e to the power z whole square dz. Now here we have applied the formula of the general method. If you remember, in the general method we had said that 1 over d minus alpha when operates on q, q is a function of x and d is d over dx. So then we had the formula e to the power alpha x integral e to the power minus alpha x q dx, where d was d over dx. Now here remember d is d over dz. So we will have e to the power alpha is minus 1, so e to the power minus z, e to the power z upon this. Now to integrate this, let us put 1 minus e to the power z equal to t. So we get minus e to the power dz, z dz equal to dt. So we will get integral minus dt upon t square. So this will be 1 by t, and 1 by t means 1 over 1 minus e to the power z. So this will be e to the power minus z divided by 1 minus e to the power z. So, when 1 over d plus 1 operates on this, we will get this. Again let us operate 1 over d plus 1 on this. Next 1 over d plus 1 operating on e to the power minus z divided by 1 minus e to the power z. Let us find out the result of this. So, again we apply this formula, alpha is minus 1. So, we get e to the power minus z integral e to the power z into e to the power minus z dz divided by 1 minus e to the power z, and this will give you how much? E to the power minus z integral dz divided by 1 minus e to the power z. Let us see how we find the integral here. So, e to the power minus z, we multiply here by e to power minus z in the numerator and denominator and get e to power minus z dz divided by e to the power minus z minus 1. Okay. Now, let us put e to the power minus z minus 1 equal to t. So, then e to power minus z into minus dz will be dt, and therefore, we shall have e to power minus z dz will be minus dt. So, minus dt divided by t, which will be minus ln t. So, this will be equal to minus e to the power minus z ln t, means e to the power minus z minus 1. Now, this will be equal to e to the power z is x. So, minus 1 over x ln 1 over x minus 1. So, this is what we get, and hence the general solution is y equal to C1 plus C2 ln x into x to the power minus 1 minus 1 over x ln 1 minus x by x. So, this is how we will solve this equation. With this I will conclude my lecture. Thanks.